Welcome! In this session, we're going to dive into an exciting problem from LeetCode, problem number 1405, titled Longest Happy String. We'll explore the challenge, break down the approaches to solve it, and highlight important concepts along the way. Let's get started. In this problem, we are tasked with constructing the longest possible happy string using a given number of A's, B's, and C's. A happy string is defined as a string that does not contain three consecutive occurrences of the same character, such as AAA, BBB, or CCC. The input to the problem consists of three integers, A, B, and C, which represent the maximum number of times the characters of B and C can appear in the string. The output should be a single string that adheres to the happy string condition, and if multiple valid solutions exist, any of them is acceptable. The goal is to maximize the length of the string while ensuring it remains valid. Let's look at an example. Suppose the input values are A equals 1, B equals 1, and C equals 7. A possible output for this case is the string capcac. Here, the character C appears the most frequently, but it never occurs more than twice consecutively, which ensures the happy string condition is maintained. For example, the sequence CCC is avoided by interspersing B's and A's strategically. It's important to note that other valid solutions, like cacac, could also be generated, as long as the happy string rules are followed. Now consider a second example with input values A equals 2, B equals 2, and C equals 1. In this case, the output string could be ababac. This string alternates between A and B, ensuring that neither character appears more than twice consecutively. The single C is placed at the end, which respects the maximum counts for each character. Another valid solution could be bababac, as long as the same rules are applied. The key is to distribute the characters carefully to avoid three consecutive repetitions. In a third example, the input is A equals 7, B equals 1, and C equals 0. Here, the output string could be aba. Since there are no B's or C's available, the solution must use only A's while ensuring that no three A's appear in a row. This results in breaking the sequence with a single B to meet the happy string condition. This example highlights how the solution must adapt to scenarios with limited character options while still maximizing the string length. Finally, let's review some edge cases. If all counts are 0, such as A equals 0, B equals 0, and C equals 0, the output is simply an empty string because no characters are available. If only one character is provided, like A equals 5, B equals 0, C equals 0, the output would be AA, as it cannot appear more than twice consecutively. In cases where the counts are equal, such as A equals 2, B equals 2, C equals 2, characters can alternate evenly to produce a string like abcap. For larger values, such as A equals 100, B equals 50, and C equals 50, the output will follow a similar alternating pattern, such as a babababab, ensuring that the happy string condition is always maintained while maximizing the length of the string. To begin, let's consider the brute force approach, which, while inefficient, provides a conceptual understanding of the problem. The intuition here is to generate all possible strings using the counts of A, B, and C, and then filter out any strings that contain three consecutive identical characters, such as AAA, BBB, or CCC. Out of the remaining valid strings, we select the longest one. The steps for this involve generating all permutations of the letters up to the total count of A, B, and C, checking each permutation to ensure it satisfies the happy condition, and finally returning the longest valid string. However, this approach is computationally impractical because the number of possible permutations grows factorially with the input size. For example, with large counts of A, B, and C, the sheer number of permutations becomes overwhelming, making this approach infeasible for real-world use. While it is conceptually straightforward, the trade-off is that it's far too slow, although it can still be useful for understanding the problem or testing very small inputs. A more efficient solution is the greedy approach, which is both practical and optimal. The key intuition here is that to maximize the length of the happy string, we should always aim to use the character with the highest remaining count, unless doing so would create three consecutive identical characters. If that happens, we switch to the character with the second highest count. This strategy is guided by several key observations. First, the happy condition requires that no character appears more than twice consecutively. Second, to achieve the longest possible string, we must prioritize the character with the highest count, as long as it doesn't violate this rule.
Finally, if the top character cannot be used, we select the next highest count instead.
The steps to implement this approach involve using a max heap, or priority queue, to track the counts of A, B, and C. At each step, we select the character with the highest count, append it to the result string, and decrease its count.
If the count remains positive, we reinsert it into the heap.
This process is repeated until no characters can be added without breaking the happy condition. Analyzing the greedy approach, its time complexity is O, A plus B plus C, asterisk log, 3, because each operation on the heap involves a logarithmic cost, and we perform one operation per character in the final string. The space complexity is O, 1, as the heap only stores the counts of 3 characters at most. This makes the approach both highly efficient and optimal, ensuring the longest valid string is generated while adhering to the rules. However, the trade-off is that it requires careful handling of the heap in specific edge cases where 2 characters may have equal counts. An alternative to using a heap is to employ a custom sorting approach. Here, instead of a heap, we maintain a sorted list of characters by their counts. As we build the result string, we select either the highest or second highest count character, depending on what's valid at that point. While the steps are conceptually similar, the repeated sorting of the list makes this solution less efficient. In the worst case, its time complexity can reach O, open parenthesis A plus B plus C close parenthesis squared, which is significantly slower than the heap-based method.
Ultimately, the chosen strategy is the greedy approach with a max heap. This method strikes the right balance between efficiency and correctness.
The heap structure ensures that we always have quick access to the characters with the highest counts, while the greedy strategy guarantees that we construct the longest possible string without violating the happy condition. With a time complexity of O, A plus B plus C, asterisk log, 3, and a space complexity of O, 1, for auxiliary storage, this approach is both scalable and practical. Compared to the brute force method, it is significantly faster and more realistic for large inputs. And while the custom sorting approach is simpler to implement, it is slower due to repeated sorting operations. Therefore, the heap-based greedy approach emerges as the most efficient and reliable solution for solving the longest happy string problem, even in edge cases and scenarios with large input sizes. In this problem, we're tasked with generating the longest string possible using given counts of the characters of B and C, while ensuring that no character appears 3 times consecutively. For example, sequences like AAA, BBB, or CCC would be invalid. The goal is to use as many of the given characters as possible without violating this constraint. A brute force solution to this problem would involve generating all permutations of the string using the provided counts of A, B, and C, filtering out the invalid ones, and choosing the longest valid string. However, this approach is conceptually interesting but computationally expensive. Generating all possible permutations of the input leads to a factorial time complexity, which can quickly become infeasible as the input size grows. For instance, if we had counts like A equals 5, B equals 3, C equals 2, we'd be looking at an astronomical number of possibilities to evaluate, making this approach impractical for larger counts. Once all permutations are generated, the next step in this brute force method is to filter out any strings that contain invalid sequences, like AAA, BBB, or CCC. This would involve examining each generated string to ensure it meets the constraint of no 3 consecutive identical characters. After filtering, the remaining valid strings would be compared to find the longest one. If there are multiple strings of the same maximum length, any of them could be returned as the result. However, this method still faces severe limitations due to the factorial growth of permutations, where generating and validating each string becomes increasingly expensive as the input size increases. In terms of computational complexity, this brute force approach has a cost of O(n)(k), where n is the total number of characters and k is the time taken to validate each string. This exponential growth makes it unsuitable for real-world scenarios with larger inputs. A more efficient solution involves using a greedy algorithm to construct the string directly. This avoids the need to generate all permutations, focusing instead on building the result step by step while adhering to the constraints. The key idea is to always select the character with the highest remaining count, as this maximizes the chances of creating a longer string. To implement this, we use a max heap, which allows us to efficiently retrieve the character with the highest count. For example, if the counts are a equals 5, b equals 3, c equals 2, the heap would initially contain entries like 5, a, 3, b, and 2, c. By repeatedly picking characters from the heap, appending them to the result, and updating their counts, we can build the string incrementally. This method ensures that the constraints are met by checking the last two characters of the result before appending a new one. If adding the highest count character would create an invalid sequence, we simply pick the next highest count character instead. An important aspect of this approach is handling edge cases, such as when only one character remains in the heap. If adding this character would violate the constraint, we terminate the string construction early to ensure validity. The overall complexity of this method is much more manageable compared to the brute force approach. Operations like adding and removing elements from the heap have a time complexity of O log k, where k is the number of unique characters, which is fixed at 3 in this problem. Since these operations are performed proportional to the total count of characters, the overall time complexity is O n asterisk log k, where n is the total number of characters. This efficiency makes the greedy approach far better suited for large inputs. The greedy algorithm works well because it leverages 3 key insights. First, always selecting the character with the highest count ensures that we make progress toward the longest possible string. Second, using a max heap enables efficient retrieval of the character with the maximum count while allowing us to update and reorder the heap dynamically as counts decrease. Finally, by tracking the last two characters of the result string, we can easily enforce the rule that no character appears more than twice consecutively. These insights work together to provide an efficient and effective solution that avoids the computational pitfalls of the brute force method while still guaranteeing correctness. To implement this approach, we rely on 2 key data structures. The first is a max heap, which stores each character along with its remaining count. This structure allows for efficient selection and updating of the character with the highest count. The second is a string builder, used to incrementally construct the result string. Together, these tools provide the foundation for the greedy algorithm. Let's consider an example to see how this works in practice. Suppose the input counts are a equals 5, b equals 3, c equals 2. Using the max heap, we can systematically build the longest valid string while adhering to the constraints. We start by initializing the max heap with the input counts 5, a, 3, b, 2, c. In the first iteration, we select the character with the highest count, and append it to the result string, giving us a. We then reduce its count and update the heap to 4, a, 3, b, 2, c. In the second iteration, we select it again, since it still has the highest count, and append it to the result, resulting in AA. After updating the heap, we get 3, a, 3, b, 2, c. In the third iteration, we select b, as adding another a would violate the constraint. This gives us ob, and the heap becomes 3, a, 2, b, 2, c. We continue this process, selecting characters based on the heap and ensuring the constraints are met, until the heap is empty or no further characters can be added. The final output, in this case, could be something like ababack, which satisfies all the conditions for a happy string. Here, we start by importing the required functions from the heap module. The priority queue, or max heap in this case, is a great choice for this problem because it allows us to efficiently manage and retrieve the most frequent characters. Then, within the longest diverse string method, we initialize an empty list called max_heap. If there are any occurrences of a, b, or c, we push their negative counts into the heap along with their respective characters. The negative counts are used because Python's heap implements a min heap by default, so negating the counts effectively lets us treat it as a max heap. After setting up the heap, we define an empty result list that will store the characters of our final string. The main logic is inside the while loop, which continues as long as there are characters left in the heap. First, we pop the most frequent character from the heap. If the last two characters in the result are the same as this character, we check if there is another character available in the heap. If not, we break out of the loop because no valid character can be added without violating the constraints. Otherwise, we retrieve the second most frequent character, append it to the result, and push it back into the heap if there are more occurrences of it remaining. The original character is also pushed back to the heap to ensure it can be added later when it's valid to do so. If the last two characters in the result are not the same as the most frequent character, we simply append that character to the result. After appending, we check if there are still more occurrences of it left. If so, we push it back into the heap with its count increment by 1, since we already used one occurrence. Finally, after the loop completes, we return the result as a single string by joining all the characters in the result list. This ensures that the generated string satisfies the constraints of the problem, where no 3 consecutive characters are the same, and it's as long as possible given the input counts of A, B, and C. Here, we begin by importing the necessary packages and defining our solution class. Within it, we implement the longest diverse string method, which takes 3 integers A, B, and C representing the maximum counts of characters A, B, and C that can be used. A max heap, implemented as a priority queue, is initialized to help us always retrieve the character with the highest remaining count. We add entries for each of A, B, and C into the heap if their corresponding counts are greater than 0. Each entry in the heap is an array where the first element is the count, and the second is the character itself, stored as its ASCII value. We then create a string builder to construct the result string dynamically. Now, we enter a while loop that continues as long as the heap is not empty. The first step within the loop is to extract the character with the highest count from the heap. This ensures that we always prioritize the most abundant character. Before appending this character to our result, we check if the last 2 characters of the result are the same as the current character. If so, appending this character would violate the constraints, so we need to handle that case separately. If the last 2 characters in the result match the current character and appending it would create 3 consecutive identical characters, we check if there is another character available in the heap. If the heap is empty at this point, we break out of the loop as no valid character can be added to the result. Otherwise, we retrieve the next character with the second highest count, append it to the result, and reduce its count. If this character still has remaining instances, we re-add it to the heap. Importantly, we also re-add the original character with the highest count back into the heap for future consideration. If appending the current character does not violate the constraints, we simply append it to the result and decrement its count. If the count is still greater than 0, the character is re-added to the heap. Once the heap is empty, the loop ends, and we return the constructed string as the result. This ensures that the final string adheres to the problem's constraints while maximizing its length. To solve the problem, we start by initializing a max heap to keep track of the character frequencies. Here, we push the negative counts of A, B, and C into the heap since Python's heap implements a min heap by default. For the input A equals 1, B equals 1, C equals 7, the heap begins as -7, C, -1, B, -1, with the most frequent character C at the top. Next, we begin building the result string by repeatedly extracting the most frequent character. First, we pop -7, C, append C to the result, decrement its count to -6, and push it back into the heap. This keeps C available for future use. The result is now C, and the heap updates to -6, C, -1, B, -1. We repeat this process, appending another C to make CC. However, since the last 2 characters are now both C, we cannot add another C directly. Instead, we temporarily use the second most frequent character, A, appending it to the result to form CCA. The heap dynamically adjusts, ensuring that C remains available for subsequent steps, and the process repeats until the heap is empty. By following this strategy, the final result string becomes CCBCCBCCBCCB, ensuring no 3 consecutive characters are the same. In this example, we use the input A equals 2, B equals 2, C equals 1. The process begins by initializing the max heap with the negative counts of all characters. Here, we push -2, A, -2, B, and -1, C into the heap, resulting in -2, A, -2, B, -1, C. To construct the result string, we start by popping the most frequent character, A. Appending it to the result gives A, and decrementing its count to -1 ensures it remains in the heap for later use. The heap updates to -2, B, -1, C, -1, A. Next, we pop B, append it to the result to form A, and push it back with a decrement count. The heap becomes -1, C, -1, A, -1, B. From here, the process alternates between the available characters, appending each one at a time to avoid consecutive duplicates.
Following this strategy, the final result string is a BAPC.
This example demonstrates how the algorithm ensures a balanced use of all characters while dynamically adjusting the heap to maintain valid choices. For the input a equals 0, b equals 8, c equals 11, we begin by initializing the max heap with -8, b, and -11, c, as a has a count of 0 and does not need to be included. The heap starts as -11, c, -8, b. The algorithm extracts the most frequent character, c, and appends c to the result, decrementing its count to -10 and pushing it back into the heap. The result becomes c, and the heap updates to -10, c, -8, b. Repeating this process, we append another c, forming cc. However, to avoid 3 consecutive c characters, we temporarily use b, appending b to make ccb. This ensures that the string remains valid. The heap adjusts dynamically, keeping the most frequent characters available while maintaining the constraint of no 3 consecutive characters. By alternating between c and b, the result string is built incrementally. The process continues until all characters are used, yielding the final result string CCBCCBCCBCCBCCBB. This example highlights the importance of the max heap in prioritizing character frequencies and dynamically selecting the second most frequent character when necessary to maintain the constraints.
Here, we begin analyzing the time complexity of the solution.
The algorithm starts by initializing a max heap, which can hold up to 3 elements corresponding to the characters a, b, and c. Each insertion into the heap, or heap push, has a time complexity of O log k, where k is the number of elements in the heap. In this case, since k is at most 3, the heap initialization step runs in constant time, or O1. Next, the core of the algorithm is a while loop that continues until the heap is empty. At most, this loop will iterate n times, where n represents the total number of characters available, calculated as the sum of a plus b plus c.
Within each iteration, the algorithm performs up to 2 heap pop operations and 2 heap push operations.
Since the heap size is limited to 3, each of these operations is constant time, or O1. In addition, the loop includes other operations such as appending to the result string and performing comparisons, all of which are also O1 per iteration. This keeps the per iteration complexity at O1, even with these additional steps. Now, since each iteration of the while loop takes O1 time, and the total number of iterations is proportional to n, the runtime of the loop is O(n). After the loop completes, the algorithm joins the result list into a string using the .join result operation. This step requires traversing all n characters in the result list and therefore runs in O(n) time. Combining all these components, we find that the heap initialization step is O1, the while loop is O(n), and the string join operation is also O(n). Adding these together gives us an overall time complexity of O(n), where n is the total number of characters, or a plus b plus c.
Next, let's consider the space complexity. First, the heap can hold a maximum of 3 elements, representing the characters a, b, and c. Because the heap size is constant and does not grow with n, the space used by the heap is O1. Then, there's the result list, which is used to construct the final string. In the worst case, this list will store all n characters, making its space usage O(n). Finally, the algorithm uses a few auxiliary variables for counters and temporary storage, such as count1 and char1. These variables require constant space, or O1. Combining these, we see that the heap and auxiliary variables contribute O1 space, while the result list contributes O(n) space. Therefore, the overall space complexity is O(n), dominated by the result list, which grows linearly with the total number of characters. To put this into perspective, let's compare this approach with a naive solution. A brute force method might attempt to generate all possible permutations of the characters of b and c, and then check each permutation to see if it satisfies the condition of no 3 consecutive identical characters. However, generating all permutations would take factorial time, specifically O(n), where n is the total number of characters. Additionally, checking each permutation for validity would add further computational overhead, making this approach infeasible for large inputs. In contrast, the optimized solution used here employs a greedy strategy with a max heap to construct the result string efficiently. By limiting the heap size to at most 3 and always prioritizing the most frequent characters,
the algorithm achieves an optimal runtime of O(n), which is a significant improvement over the brute force approach.
Finally, let's analyze the best, average, and worst-case scenarios for the algorithm.
In the best case, the counts of A, B, and C are roughly equal. This ensures that heap operations and string construction proceed smoothly, resulting in a runtime of O(n). In the average case, which represents most practical scenarios, the algorithm still performs O(n) operations. This is because the heap size remains constant at 3, ensuring that each heap operation continues to run in constant time. Even in the worst case, where one character dominates the input, such as when A equals n, B equals 0, and C equals 0, the algorithm processes each character exactly once. This guarantees that the algorithm still runs in O(n) time. A mathematical proof of the big O complexity confirms that the work done per character, including heap operations, comparisons, and appending to the result, is constant. Since the total number of characters is n, the overall time complexity is O(n). Similarly, the space complexity is dominated by the result list, which grows linearly with n, giving us a space usage of O(n). On this slide, we focus on some of the most common mistakes developers encounter when solving this problem. First, overlooking base cases is a frequent error, such as forgetting to handle scenarios where all counts are 0 and no strings can be generated.
This often leads to runtime errors or incorrect outputs. Next, redundant computation in brute force solutions is another pitfall.
Generating all permutations without pruning invalid strings early significantly increases time complexity, especially for large inputs. Another issue is ignoring recursion limits when using recursive approaches. This can result in stack overflow for large constraints, which can crash your program. Lastly, mismanaging state in dynamic programming is a critical mistake. If you incorrectly index or transition between states, it can lead to incorrect results due to bad state transitions. Being mindful of these errors will help you write more robust solutions.
Now, let's delve into further pitfalls and some practical insights for interviews.
Forgetting to optimize string operations is another common challenge. For instance, if you're concatenating strings inefficiently within loops, this can escalate the time complexity from O(n) to O(n squared, which is highly inefficient. Shifting to interview strategies, it's essential to identify patterns. Problems that constrain consecutive characters often require tracking recent states, such as using a sliding window or dynamic programming. Additionally, while it's okay to start with a brute force approach to explain your thought process, you should always discuss its inefficiencies and propose optimizations. Recursive backtracking is a common technique for generating constraint-based strings, and interviewers may expect you to optimize it using memoization. These strategies will showcase your problem-solving depth. Effective communication is key when explaining your solution. For example, you need to clearly articulate how you handle constraints like avoiding consecutive sequences of AAA, BBB, or CCC while generating the string. Moving on, let's look at related problems that share similar patterns. LeetCode 1415, which involves finding the kth lexicographical happy string, is directly related and can help you understand the constraints better. LeetCode 22, generate parentheses, is another classic example of constraint-based string generation. Similarly, LeetCode 526, beautiful arrangement, and LeetCode 93, restore IP addresses, involve constructing valid outputs under specific rules. Exploring these problems can deepen your understanding and prepare you for variations in interviews. Finally, let's discuss some alternative approaches to solving this problem. Backtracking with pruning is a more efficient method than brute force, as it avoids redundant work, but it requires careful implementation to ensure correctness. The time complexity here depends on factors like the branching factor and recursion depth. Dynamic programming is another option. While it demands significant pre-computation and memory, it eliminates redundant calculations and is particularly well-suited for problems with constraints like avoiding consecutive characters. Greedy construction is a faster approach for simpler problems, although it may fail to handle more complex constraints. Lastly, iterative string building can be a straightforward method that's easier to debug, though it might be less intuitive when dealing with constraint-heavy scenarios. Each approach has its trade-offs, and selecting the right one depends on the problem context and requirements. Thank you for following along. Today, we reviewed the longest happy string problem and explored how a greedy approach can efficiently solve it.
Remember to practice similar problems to strengthen your skills.
If you enjoyed this session, please like and subscribe for more coding content.
See you next time. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!